Okay, so we will study or run the Bellman-Ford algorithm using this directed graph. Okay, so this graph is from Corman's book, but they have not shown the steps, so it's difficult to understand if you just read from the book. I hope after you have seen this video, probably it will be easier to understand, and I'll always be available in the office hours and other, by other means to answer any questions you might have. We can see one more example or two more examples to clarify the concept in a better way. So this is a directed graph. The number of vertices are 5: S, T, X, Y, and Z. Okay, 5 vertices. So so here I have listed the ages of the vertices. If you remember the Bellman-Ford algorithm, so we have to have how many iterations? We have to have mod v minus 1 iterations, mod v minus 1. So here mod v is 1, 2, 3, 4, 5. So 5 minus 1 equal to 4 iterations we need. Okay, so that's one reason I choose this graph, because it needs 4 iterations and I have only 4 colors to show you the iterations. Okay, so 4 iterations, and we have to list the ages and relax them in that order. So writing the ages does not need to follow any order. Please understand that. I just wrote it in the alphabetical order, starting from S to T, ST, SY, and then TX in that alphabetical order. So that's all. There is no other specific order. You can write in any order you want, and the final result still should be the same. So do not worry about this. You should not have any question about that. I am deleting this thing. How many iterations? You always remember is mod v minus 1 iterations. So we will kind of relax the ages in that order. Okay, so let me kind of write it. Iteration 1 will be ITR1 using blue, and then ITR2 using red, just so that I remember. ITR3 using black, and ITR4 using green. Okay, I hope green is visible there, and let's see that. So I put the pens in that order also so that I don't forget it. And here one more thing I want to show you, that I have given this, the distance matrix. If you remember that initially what happens when we do the initialization, INIT initialize, S is 0. If you remember, S is 0 initially, and all other vertices. So let me make this one S inside this, it's just for the sake of simplicity. Y, Z is inside this, and X is inside this. Okay, so now what happens? The in distance estimate, that we will have all of them infinity. Okay, so this is just the distance table. So this is infinity, this is infinity, this is infinity, and this is infinity. Okay, initially, and this is 0. So that's the distance estimate, and this is like it's like a parent table. You can call it parent table, just to say keep track of it. People do not really do that. I just want to do that just to show you that which age will set the parent of a node. That's for the easiness. So I'll try to do that all the time. If I do not do, I'll kind of come back and do that. So I cannot tell you to remind me that kind of, I miss my students. If you remind me if I miss something, that's always easier for me to do. Anyway, let's move on. Let's start. Blue is the iteration 1. Okay, so the iteration 1, all these ages have to be relaxed in that order. So iteration 1 is, let's consider S to T age. So as we know that we have to relax, so what we do, 0 plus 6 is 6, which is less than infinity. So this distance estimate is higher, so I replace it with 6. Okay, so this age is done, and this is kind of relaxed. That's why I put this down arrow means the weight estimate reduced. So people do not do this kind of thing. It's just to show you that this worked. And now t's parent is s. So t dot pi equal to s. Okay. Now you see similarly here y here this 0 plus 7 is 7, which is less than infinity, so this one will also change. So s dot y also the distance estimate is reduced. We got a shorter distance estimate, so y's parent is also s. Okay, so now what about tx? Tx we cannot do at this iteration because we do not have the distance estimate. Okay, so that will be the next level. So we cannot do any of them because their distance estimate is not known to us. So when we so at the end of iteration 1 I t r 1, the distance estimates are like s is 0 and t and y are 6 and 7 respectively. T is 6, y 7, remainder remains infinity. Okay, I hope you understand this. Okay, so that means at the end of the iteration 1, so these are two parent nodes, so this s to t, and in the book you will see that figure b in page 652, figure 24.4b. Okay, it shows that only at the end of iteration 1 what are the ages and stuff like that. So that's not very easily understandable. Now let's go to the iteration 2. Okay, so iteration 2 we start with red pen. So this is we will again go in the same order. S to t is 6, so nothing, no better distance estimate, so we don't do anything, we put a line. Okay, so similarly s to y is also same distance estimate, nothing to change, so we put a dash. And then let's go to I mean here we could have put a dash for all of them like this, you know, on that way. So now for what happened, so after that t2x, okay, t2x, this is now 6, t's distance estimate, t2x is 6 plus 5, 11, so that's less than infinity, so we change it to 11 and we put a downward arrow here. And x says new parent is t. Okay, so x dot pi equal to now t. Okay, so now you see what else, what's the next one, t to y. T to y is 6 plus 8 is 14, which is more than 7, so we do not do anything, we just put a dash here. Now it's t to z. T to z is this 6 plus 6 minus 4, that is 2. So z's new distance estimate is 2. 6 minus 4 is 2. So z dot pi is equal to now t. Okay. So and t dot z, it's a this reduce. So I put a down arrow here just to remember. That's all. No other reason. Okay. We just have to do it in that order. That's all. We do not need to put this down arrow dash. It's just for explaining you so that you can easily understand, easily follow. Now x to t is that's the next one, next age to relax. Where is x? Yeah, here x to t. Oh, it's minus 11 minus 2, that is 6. So 11 minus 2, that is 9, but this is 6, so this no need to do anything. Okay, x to t, nothing to do. Y to x, y, this is y to x. Y to x. Okay, yeah, 7 minus 3, that is 4. So now this is 11, so we get a cheaper distance estimate. Okay, so we change it. Y to x is now changed, and it's at the same rate we will also change this one. So now x dot pi, x's parent is y because you got a cheaper distance estimate. So this changed to y, you see. I did not delete it, I just skip it and make it to y. And so this is done. So now we go to y to z. Y to z is 7 plus 9, which is much higher than 2. So we don't do anything. Z to x. Z to x is 2 plus 7, 9, which is more than 4. So we don't do anything here as well. Z to s, that's the final Z to S is 2 plus 2, 4, but this is 0, so definitely that is less, so we don't do anything here also. So the second iteration is complete. Okay, second iteration, at the end of iteration 2, what is the distance estimate? Let me write it here. Okay, so for S it is still 0. For T it is 6. Okay, 6 is there. For X it is 4. For Y it is 7, and for Z it is 2. Okay, so this is the new distance estimate for this vertices in this graph using Bellman-Ford algorithm. Now let's go to the iteration 3. Okay, so now the color is black, so we go for the iteration 3. So in the same order of vertices we'll consider, same order of edges. So S to T, there is no new distance estimate. S to T is 6, so the distance estimate remains same, nothing to do, put a dash. S to Y is also 6 and there's 7, no changes there. T to X, T is 6 and T to X is 6 plus 5, 11, but you have a cheaper distance estimate, nothing to do here. T to Y is 6 plus 8, it is cheaper, nothing to do there, put a dash. T to Z is, where is T to Z is 6 minus 4, 2, we already have 2, nothing to do here. X to T is 4 minus 2, which is 2. 4 minus 2 is 2. See, now we have a cheaper distance estimate for T. So X to T actually reduced. So I put a downward arrow, and at the same time, now T's parent will change to X because we have a cheaper path through that. From S we change to X. Okay, so I hope you are following. Now let's continue. Y to X, where is Y? Y is 7. Y to X is 7 plus 2, 9, but 7 minus 3, 4. That is already there, nothing to do. Y to Z is 7 plus 9. We definitely have something cheaper, which is 2, nothing to do. Z to X is 2 plus 7 is 9. We have a 4, which is cheaper, nothing to do. Z to S is 2 plus 2, here, nothing to do. Okay, so we just only one change. Now we go for the fourth okay, sorry, I forgot to do this one. Iteration 3 is distance estimate. S is 0, T is 2. Okay, T has changed, you see, every stage something is changing at the end of every iteration. Now T is 2, X is 4, Y is 7, and Z is 2. Okay, Z is 2. Okay, so now let's go for the iteration 4, and iteration 4 is using green color. S to T, this is, we have a cheaper distance estimate, so this one, nothing to do. I hope you can see the green color. And then we have S to Y, which is 7, nothing to do, no reduction. T to X, T is 2, then T to X is 2 plus 5, 7, but we have a 4, nothing to do here. T to Y, which is 8 plus 2, 10, we have a cheaper distance estimate already, nothing to do. T to Z is 2 minus 4. 2 minus 4 is minus 2. So Z now has a cheaper distance estimate, which is minus 2, you see. T is 2 and this edge is minus 4. So that is minus 2. So this has reduced T to Z. T to Z has reduced. And here you see now Z's parent will be T. Z dot pi, okay, Z's parent was already T, so nothing else to do. So this is still T, and now from X to T, X is 4, X to T is 4 minus 2, 2 already there, nothing to do. y to x is 7 to 7 minus 3 4, that is already there, nothing to do. Y to z is 7 plus 9, which is definitely higher, so nothing to do. Z to x is minus 2 plus 7, that is 5, that's still higher, nothing to do. Z to s is minus 2 and 2 0, so we already have a 0, so nothing to do. So there is only one change here, and we have finished 4 iterations. We are supposed to do 4 iterations, and if we do a 5th iteration, you will see if the algorithm is correct, there will be no more change. Okay, I forgot to write this, let me write that, and probably I will show you another iteration 4. Okay, so iteration 4, what happened at the end of iteration 4? S is 0, t is 2, y is 7, x is 4, y is 7, and z is minus 2. Okay, minus 2. So these are the distance estimate. Now let's go for another last, just to show you that even if you do another iteration, there will be no more changes. So let's do it with purple. So this is iteration 5. So I put a star with it. It means you do not need to do that. You do not need to do that. These are the main iteration. Okay, these are the main iteration. You do not need to do that. I can even put a cross just to show you that it will not make any changes. See, S to T is 6, so no change here. So we have a cheaper. So S to this is 7, so no change here. T to X is 2, 5, 7, so it's no change here. T to Y is 2 minus 4, which is minus 2, already there, no change. T to Y, sorry, T to Y, yeah, T to Y is now changed, T to Z is also no change. Okay, then X to T, X is 4 minus 2, that is 2, no change. So Y to X is 7 minus 3, which is 4, no change. Y to Z is 7 and 9, so no change. Z to X is 7 minus 2, which is 5, we have a 4, so no change. And Z to S is minus 2 and plus 2 is 0, which already we have, so no change. So what I wanted to show you, that if we write another iteration 5, you will find that there is no change. Okay, so it's still 0, 2, 4, 7, minus 2. That means the edges have already been relaxed to the maximally possible value, and one more iteration will not make any difference. So here, this is the end of one example of a Bellman-Ford algorithm. As I said, number of iterations should be mod v minus 1, so that is 4 minus 1 equal to 3, and we do not need this last iteration. This is just to show you that after 4 iterations the graph already does maximum relaxation. Now using that parent pointer, we can draw the that how the tree, shortest path tree is t's parent is x, so this one, y's parent is s, so this is the path, and then t's parent is, where is t? T's parent is x. Okay, so t's parent is x, so this is the edge which made it maximally relaxed. Then x's parent is y, so then this is the edge which made it maximally relaxed. Y's parent is s, we already done that. Z's parent is t, so this is this red ones shows which path you have to follow to get the shortest path tree. Okay, so this is like from S you go down to Y, from Y you go up to X, from X you go to T, and from T you go to Z. So this is the shortest path tree of this graph, S, T, T. Okay. I hope you understood. Thank you.